Hello and welcome to this video on what to do about factor loadings greater than 1 in CFA. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials, usually related to multivariate statistical analysis such as factor analysis, structural equation modeling, multi-level analysis, or latent class, latent profile modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional free resources, including a link to my weekly statistics newsletter, as well as free courses and other courses that I offer for QuantFish. In this video here, I want to talk about factor loadings greater than 1 in confirmatory factor analysis, which confuse many people. So let's talk about this. Here I have a factor model, a simple factor model, with a single factor and 3 indicators, and you can see that in the standardized solution that is depicted here in this diagram, you can see that there's one factor loading that is 1.255, and that's the factor loading of the first indicator y1, and you can see that that indicator also has a negative error variance of negative 0.575 attached to itself, with a non-defined standard error that is given here as 999.000 by Mplus, which indicates that the standard error could not be computed. So you can see that this is an improper solution. Obviously, we also call that a Haywood case when you have a negative variance estimate or a negative residual variance estimate in a structural equation model or factor model. Then that is an improper parameter estimate. Variances by definition cannot be negative. It has no meaning for for variance to be negative. That could not be interpreted, and so therefore this is an impossible, inadmissible, improper parameter estimate. We call that a Haywood case also in structural equation modeling, and so this here is associated with this standardized factor loading that is 1.255, and I want to shed more light on this issue in this video. So what does this mean? Why does this occur? And what can you do about it? So let's take a look at the output file here in a little bit more detail for this particular model. So I'm switching over to the Mplus output file, the print output, where you can see in the standardized model results section that here we again see this improper factor loading of 1.255. And so let's talk about, first of all, why is this improper? Why is a factor loading, a standardized factor loading of 1.255 in this model an improper solution that is associated with a negative error variance? The reason for this is that this is a simple structure CFA model, meaning each variable loads only onto one factor, and here there is only one factor, but it would be the same principle if you had a CFA model with multiple factors and each variable loaded only onto one factor. Then the factor loadings, the standardized factor loadings, can be interpreted as correlations between the variable and the factor. And we know that correlations are bound by -1 and +1. So correlations can only vary between -1 and +1, and -1 would mean a perfect negative linear association. +1 would indicate a perfect positive linear association. And so something greater than 1 doesn't make sense. So a correlation of 1.255 doesn't make sense, whereas a correlation of 0.717 does make sense. Also a correlation of 0.558 also makes sense and is interpretable for the other 2 indicators. But this is clearly not interpretable as a correlation, and therefore it is improper. Now, 2 important points here. First of all, this concerns the standardized solution. Here you can see I'm in the standardized model results section of Mplus. STDYX means it's the completely standardized solution where both the outcome variables or Y variables as well as the exogenous or independent variables X are standardized, which means in this case both the X factor, so the factor here is the independent variable, is standardized. As you can see here, the variance is fixed to 1 with no standard error and no test statistic and p-value, because this is a fixed parameter. And also the observed outcome variables, the Y variables, are also standardized here. So all variables are standardized to a variance of 1, and that's why those factor loadings are interpretable as correlations, and therefore in this model they're not allowed to be greater than 1 or smaller than -1. That's the first important point. The second important point is related to that. It does not concern the unstandardized solution. So when we scroll up in Mplus, the first solution that's actually presented by Mplus for a CFA or structural equation model is the unstandardized solution. In the unstandardized solution, the observed and latent variables need not have a variance equal to 1.0. So they can be in a different metric with variances that differ from 1.0. And therefore, the loadings here, they are allowed to be 1 or greater than 1. They could even be 50, and it wouldn't necessarily mean anything. If the metrics of the observed variables differ strongly from one another, so let's say you have one indicator of depression that varies between a score of 0 and a score of 500, and then you have another indicator of depression that only varies between 0 and 10, then those indicators would have very different variances, potentially at least, and therefore also they might have very different loadings, some of which may not be equal to 1.0 or maybe greater than 1.0. So for the unstandardized solution, this rule does not apply. The loadings here are allowed to be greater than 1. That wouldn't be a problem, at least not necessarily. We're talking about the standardized solution. Okay, so and in this case, in the standardized solution in this model, that loading is not allowed to be greater than 1. Now later we will see that there's a third important point that makes matters more complicated, and that is under certain conditions actually the standardized loadings also are perfectly legitimate to be or allowed to be greater than 1. But that's a point that I will discuss towards the end of this video. Let's take a look at this model in a little bit more detail for a while. So again, we're now in the standardized solution STDYX, fully standardized, and we can see that there's also a negative residual variance estimate associated with Y1, and that has to be the case. So whenever you get a standardized factor loading greater than 1 or smaller than -1 in a model like this, where each variable loads only onto one factor, then there must also be a negative error variance, because if the correlation between the variable and the factor is estimated to be greater than 1, this means that the factor explains more than 100% of the variance in that indicator. Remember that the correlation squared gives you R squared, right? So meaning this loading, since it's a correlation between Y1 and F, if we square that correlation, that would give us R squared, and that would give us the proportion of variance that is accounted for by F in the variable Y1. So this would mean 125.5%, this squared, so this correlation squared, so 1.255 squared, which would be a value above 1, would indicate, so say, what percentage of variance is explained by the factor. And you can see that this R squared that Mplus would normally print is undefined here, because it would be a value greater than 1. Namely, it would be this value squared. And Mplus then at that point decides, well, this doesn't make sense to have an R squared greater than 1, because it would mean more than 100% explained variance in the variable, and therefore Mplus prints undefined here under r squared. And so this is why you get the negative error variance, because it would mean that the variable has less than 0 error variance. Otherwise, you couldn't have more than 100% true score variance or 100% factor variance. And so the whole thing doesn't make any sense, right? So clearly this is improper. It means to say the solution cannot be used. Now, the next question is the why. Why does this happen? And there are several reasons why this can happen. One reason can just simply be bad luck, sampling error. So you have a sample where randomly this sample contains a weird composition of cases that results in an awkward, so say, covariance or correlation matrix where the covariances and correlations are such that they produce a solution like this, even though the model may be the true model. So even though maybe the data generating process here that underlies this correlation matrix is truly a one-factor process, but simply due to sampling error, simply due to chance, you ended up with a covariance matrix that produced this improper solution. So it's simply bad luck. There's really not much you can do in that case. Now, typically this doesn't happen until you have, or unless you have a small sample. So it's often a small sample problem, because with small samples we have more sampling error. There's more chance that, or greater chance that we will end up with correlations and covariances that are off relative to the population covariance matrix due to sampling error. So that perpetuates this problem or exacerbates this problem when you have a small sample. So small samples are more prone to improper solutions, so if you can, avoid small samples. Furthermore, what also is a problem is when you have few indicators. So this is more likely to happen when you have factors that have only 2 indicators. So having more indicators is also something that can help prevent this problem. So having at least 3 indicators per factor makes it less likely that you will run into an improper solution. Now, here you saw, despite the fact that we have 3 indicators, we're still running into this problem. And in fact, this model is actually saturated. So this is a model that fits the data perfectly by definition, because a single factor model with 3 indicators is always just identified when you estimate 2 of the loadings, and so this model is saturated, and you can see that from the fact that you have 0 degrees of freedom here for the chi-square test, and the chi-square value is 0, indicating perfect fit. So even for such a model, this can actually happen. So then what is the issue? Here we're not, so the sample is also not particularly small. When we take a look at the sample size, it was actually 1,000 observations, and so this isn't clearly isn't a small sample problem in my example here. And then really the only other explanation is the composition of the data, so to say, not being in line with the model. And so, in other words, model misspecification. And in my experience, this is also actually the most frequent cause of improper solutions, is when you fit a model that is incorrect for your data. And so here, this is actually an artificial correlation matrix. It's simulated data. And so you can see here that the correlations, which are depicted here, are not in line with a single factor model. You have 2 variables that are very highly correlated, y1 and y2, and then also y1 and y3 are also still very highly correlated, but y2 and y3 are not very highly correlated. So there's an inhomogeneity in the correlation structure here, such that the idea that the 3 variables are unidimensional, that they measure a single factor, is not plausible. And so we can't here reject this model because it's a saturated model. We have only 3 indicators, only 1 factor. And so therefore the model will still trivially fit perfectly, but nonetheless it is misspecified. And so this misspecification then is shown not by fit statistics, but by the parameter estimates, where some of them are improper, in this case the standardized loading and the standardized residual variance. So this shows you the model is misspecified. It doesn't work here to fit a single factor structure to these three indicators. They are not unidimensional. You would have to pick a different model or select different indicators in this case, because this clearly indicates that there's model misspecification. So the take-home message here, or one take-home message, is then that when you encounter an improper solution, meaning a standardized factor loading greater than 1 in a model like this, in a simple structure CFA model, then it most definitely has something to do with model misspecification. You have to rethink your model specification unless it can be explained by a small sample or a small number of indicators. Now, to make matters even more confusing for you, I will now show you an example where standardized factor loadings greater than 1 are actually perfectly okay and perfectly reasonable. And that is when you have special factor models that are not simple structure factor models. And I'm going to show you an example here, which is a linear growth curve model for longitudinal data, where we use CFA to fit an intercept factor and a slope factor to a repeatedly measured observed variable y. So here y1, y2, y3 and y4 are not different indicators, but they are the same indicator measured repeatedly across 4 time points. And we're now fitting a growth curve model where the variables all load on the intercept factor with an unstandardized loading of 1.0, and where the variables at time 2, time 3 and time 4 also load on a slope factor with loadings 1, 2 and 3. Notice that then that y2, y3 and y4 have loadings on 2 different factors, on the intercept factor and on the slope factor. And also notice that the intercept and slope factor are allowed to correlate. You can see here this is the covariance between the intercept and slope factor that was estimated here. Now let's take a look at the Mplus output file for this model, and we will see here, when we go to the growth curve model output, we'll see that now in the standardized solution we do have factor loadings that are greater than 1. So y2 has a factor loading greater than 1 on the intercept factor, and y3 and y4 have factor loadings greater than 1 on the slope factor. Now in this situation, those are perfectly fine and not indicative of any kind of improper solution, as you can see from the fact that there aren't any negative residual variances when you go to the residual variance section, and also there are no undefined r-squared values here. They are high, some of them, but none of them are improper or greater than 1. Also, Mplus for this model does not issue a warning message, which it would for any kind of improper solution, where it would tell you that there's something wrong with your model. So, interesting. We have standardized loadings greater than 1, but here they are not a problem. Why is this? Now, notice that in this model, when we take a look again at the unstandardized model results for a second, notice again that variables here have double loadings. So y2, y3 and y4 load on the intercept factor with an unstandardized fixed loading of 1.0, and they load on a slope factor with fixed loadings of 1, 2 and 3. So therefore, it's not a simple structure CFA model where each variable has only one loading on one factor. Here we have 3 variables that have double loadings, and moreover, we also have a covariance between intercept and slope. Notice that the covariance here is estimated to be negative, which is often found for growth curve models because the intercept or initial status is often negatively correlated with change across time, meaning people who are high on something, they often change less. So say due to a ceiling effect, they have less room for growth than people who are lower, and so therefore there's often a negative correlation between intercept and slope factor. And so when that is the case, then it can happen that the factor loadings here become greater than 1 because they are no longer interpretable as correlations between intercept and slope factor. So it's no longer the case that this value for y2 of 1.094 is a correlation. Instead, it's a partial standardized regression coefficient. So it's like in multiple regression where you have multiple correlated predictor variables. Here in a growth curve model, y2 is a function of both the intercept factor and the slope factor. It has loadings on both, and there's a covariance between intercept and slope factor. And so therefore, these coefficients here are not correlations. They are partial standardized regression coefficients, and partial standardized regression coefficients are allowed to be greater than 1 or smaller than -1, as you may know from multiple regression analysis. In multiple regression analysis, we find standardized regression coefficients greater than 1 or smaller than -1, oftentimes in the case of suppressor variables, when we have highly correlated predictor variables, when there are suppression effects, effects of multicollinearity, then we see sometimes that standardized regression weights are greater than 1 or smaller than -1. And so this can also happen in a model where you have correlated factors and where you have cross-loadings of indicators on multiple factors, and then that can be perfectly fine and is not a reason to be concerned. I hope you found this video useful to learn more about standardized factor loadings greater than 1 in a CFA, in which context they do indicate an improper solution, in which context they do not necessarily indicate an improper solution. And if you did, then please hit the like button, check out the description for additional resources, leave a comment in the comment section, and I'll see you next time.